So let's solve the next example, probably to make it clearer. This example says 1 is a limit point of the set, and the set was given as 1 over 2, 2 over 3, 3 over 4, so forth, so on and so forth. Now, you realize that 1 over 2 is the same as 0.5, 2 over 3 is the same as 0.67, 3 over 4 is 0.75. The next one will give you a number higher. But what this series tries to show you is that you would continually approach a number very close to 1, but you will never get to 1, right? And that's the whole point of this sequence. And that actually explains this line of statements here, right? That for for delta greater than 0, for each x, which is a member of A such that 0 is less than x minus L less than delta, it means that anytime you take the limit point from any element of the set, right? You are still within the neighborhood of the set. That is, even though you have deleted some elements of the set, you are still within the range of values accepted by the set. Now, we will see its relevance when we are considering a finite set, right? So, and here the statement goes, it says, no finite set has a limit point. Why? Example, this set 1, 2, 3, 4, 5 has no limit point for any suggested number. A deleted neighborhood can be constructed with no element of the set present, right? So now one thing you have to take note about limit point is we are mainly talking about existence, right? So let's assume for a very small delta, right? So let's assume a delta of 0.1, right? And let's say the limit point is 3. Now, when we assume that the limit point is 3 and a delta of 0.1, you realize that we can have regions of what? 2.9, and we can have regions of what? 3.01, right? You realize that this is a what? A finite set. There was no 2.9 inside, there was no 3.01, right? So this set can't have that limit point. Remember, delta has to be small enough to satisfy this condition, right? Delta has to be small enough to satisfy this condition. So that's what you see. Now, an infinite set may or may not have a limit point. In particular, natural numbers, they have no limit points, right? If a set contains all of its limit points, it is called a closed set, right? And this is also another point of confusion, but just take note. When it is drawn, right, or when the representation is drawn such that you see this square brackets, right, it means that this 0 and this 1, they are part of the set, right? Now, when you see this, shall I say, circular bracket or the normal bracket you use, when you see this one, it means that 0 and 1 are not part of this set, right? So if I'm describing this set, I'll say 0 is less than x, less than 1, right? What it means is that 0 is not part of the set, right? But the only way we can define it is by showing you that it is somewhere around 0 and 1. That's what we are seeing. Now, it is not a closed set since 0 and 1 are not limit points. So when you see something like it's not a closed set, this is a closed set because it contains all of its what limit points. So for example, 1 is a limit point of the set, so can you say 0, right? Now another question arises: how many limit points does the set minus 1 and 1 have? Why is 0 a limit point, right? Now this is pretty simple. How many limit points does it have? Well, this set has infinitely many limit points, right? For example, if I choose 0 as a limit point and I choose a delta very small enough such that it satisfies the condition above. So let me choose a delta of say 0.5. You realize that if I choose 0 as the limit point and a delta of 0.5, realize that if I subtract, I get minus 0.5. If I add, I get what? 0.5. I realize that these two elements are also elements of this set, right? so it is element point. Now the next questions think could be left out of an exercise, right? But continually answer them. I will share the answer in the link description. But answer them and let's compare your solution. So let's move on to bounds. Yes, you can take the remaining ones as examples for yourself. So let's move on to bounds. Now let A be a set. If for every m such that x is less than or equal to m, there exists an x which is a member of A, then A is said to be bounded above. Right. These are mathematical statements. They usually sound funny, but they're actually simple to understand. It's just saying that if you have a set and there is a real number, you are calling the real number m, right? And such that every member in the set, right, is always less than or equal to that real number m, right? The set is said to be bounded above. Now, in reverse the statement, it works for what's bounded below, right? So, let's see an example. The set 0, 1 is a bounded set since, for example, -2 less than x less than 3 will make such that for all x in this 0, 1, 0, 1 will be in this range. So what they are saying is that if you list elements of this set, all the elements of this set, you can assume your m, that's the lower bound, to be -2, the upper bound to be what, 3, and every element of your set will be in this range, right? They just choose arbitrarily. Now the set A equals 1, 1 over 2, 1 over 3, 1 over 4, up to 1 over some large number forever. It's bounded because you realize that always -1, no element of this set will be lower than -1, right? So the set is bounded below. And so you can say the least upper bound is 1 and the greatest lower bound is 0. So here is what it means. The smallest number for which all elements of the set will be less than is the least upper bound. So for example, will be less than or equal to the least upper bound. So for example, all the numbers of this set, right, will be always less than or equal to 1. So that's the least upper bound, right? Now, also, all the elements of this set will be greater than or will be greater than 0. So that's what's greatest lower bound. It's kind of a misnomer, but that's how the mathematics defines it. So hope you're able to keep it. Then another interesting theorem appears, and it's called the Bolzano-Weierstrass theorem. And it sounds scary, but it's actually a very simple one. So it states that every bounded infinite set has at least one limit point. So this is what it's saying. If I have a set, right, and the set is infinite. Now I showed you that a set can be bounded and infinite. So for example, the set of 0, 1, even though it's bounded, is infinite because you don't know the number of rational numbers between 0 and 1. If you say there are 2, say 0.5, and then I can also say, then what about 0.05? Because between any two rational numbers, I can find a second rational number. So this is, although it's infinite, it is bounded, right? Now what the Bolzano-Weierstrass theorem is saying is that every bounded infinite set has at least one limit point, right? So when you see a set and you can either identify that it can have a lower bound or an upper bound, then it means the set has a limit point, right? So for example, they are given a proof. They say show that S of n is equal to 1 over n, where n is equal to this number, satisfy the Bolzano-Weierstrass theorem. So it's as simple as that. Now you were given a formula, right? So start showing the formula by proof. The formula says do 1 over n. So the first part, 1 over 1 is 1. 1 over 2 is 1 over n here will be what? 1 over 2. Then 1 over n here will be 1 over 3. Continually. Now you realize something. You realize that this set or this sequence is bounded above by 2 and bounded below by -1. It's usually when they are just justifying their boundaries, they give numbers which are far above the least upper bound and the greatest lower bound, right? So although these 2 and -1 are not exactly the least upper bound and the greatest lower bound, are not exactly that. We just want to show that the set is bounded, right? And now you realize that this sequence will never what exceed 2 or be smaller than what -1. Hence, we say that the set S is infinite since it can be placed into a one-to-one correspondence with a subset of itself. Remember the previous one, because if I pick from 1 to 2, right, there exists infinitely many numbers between them, right? And each of those infinitely many numbers, between any two of them, there also exists infinitely many numbers between them. So that's the one-to-one correspondence with itself, right? And because the set is infinite and can be placed with a one-to-one correspondent with itself, it is what countably infinite and countable, right? So because of that, and secondly, because it is bounded, then it satisfies the Bolzano-Weierstrass theorem. So it's not anything difficult. All you have to show is that the set is one bounded, and also it's it has at least a limit point, right? And as easy as that, you have your answer. So for example, they showed it that you can list the elements of the set above, right? You can list it 1 half 1 over 3 going. Then you can come and list a subset of it. So a subset of it means instead of starting from 1, you start from 1 over 2, right? So 1 over 2, 1 over 4, 1 over 6, 1 over 8. You realize that they can be placed, the subset can still match up, like the countability of the subset can still match up with the countability of the mother set. That is what the one-to-one correspondence means. So you realize that since it can be done with that, then this set is not uncountable, it is countable, right? But in as much as it's countable, it is what? Bounded, right? And so you realize that the limit point is 0 because that's the least lower bound. No element will get to 0. And they show examples of giving the deleted neighborhood. Realize that it is clear that for every delta, there will always be an integer such that 1 over n minus 0 will be less than delta. And the next time we come, we'll go into this proof. So thank you very much. You can like, share and subscribe the video as well. See you next time.